Okay. Hello, everyone. Thank you for joining me today. My name is Chenfeng Wei. I'm a PhD from the University of Manchester. I'm a fourth-year PhD. My PhD is sponsored by the industry company, and they asked me to build a framework for analyzing smart contract. So nowadays, I'm trying to analyze smart contract and combining large language model and the formal method all together. So that's my research object. And the speech will be outlined in 3 parts. So the first part will be explain my just published paper and to show what we have done. And then the part 2 is going to talk about what we are going to do. So we want to extend our work. And the third part is a general thought, like beyond smart contract, beyond this bug reproduction topic, how we can combine large language model and format. Oh, by the way, I forgot to say the title. So the title is VeriExploit, automatic bug reproduction in smart contracts via large language models and formal methods. The paper is published in ASC 2025. Okay, so let's first go for a background. So it's basically an explanation for the people who have no idea what a smart contract is. So a smart contract is basically something similar like a C++ class. So a contract is a class, and the variable is the data member, and the function is the methods. So the only key difference is that a smart contract don't have a determined entry point. They don't have a main function. So since there's no determined entry point, so a typical bug detector would expect any possible implementation of such main function. So they will expect maybe you should call A function first, or they will expect you can call B function first. So they will expect anything. So that's the precondition. And in our topic, trying to reproduce a bug, basically we find a bug and we want to reproduce this. Basically, we are trying to find that main function that could retrigger the bug. So that main function will be written in another contract. So it's a contract form. Another background is what a bug reproduce look like. So the left-hand side is the manual analysis. So you given a contract which is non-vulnerable. So how you decide exploit path to retrigger the bug. The right-hand side is the typical report from a bug detector in smart contract. So we can see a gap here. So maybe it's a little bit difficult for the guy who don't have knowledge of smart contract. But the general, the core idea is, you can see the left-hand side, there are 2 contracts. They are interacting with each other. So you have an attacker and you have a target. So the attacker calls something, and then the function call then pass to the target contract, and target contract call back to the attacker. So there's an interaction. But in the right-hand side, so you only have the vulnerable contract, and you send it to the bug detector, and you find the bug. That's good. But when you actually look at the log file, basically the trace here, you cannot find the attacker. So you don't know how they interact. You only know, okay, you find a bug, what the bug type is. But you can think everything have been synthesized as a model, a formal model. So it's not quite clear. So if you find a bug by a verifier and you're trying to reproduce it, then you find a trouble. That's the thing we want to tackle. So here's our motivation. So reproducing a reported bug, it can be difficult, particularly for smart contracts, because like verifier, they detect issues, but they rarely provide executable reproductions. So you have limited or abstract information from the verifier, but you want to create a concrete runnable POC. Basically, it's another contract. So you want to create a contract, not just limited information. And what's worse is that many smart contract bugs, they have to be triggered we are a cross-contract interaction. Basically, you need to have a multiple contracts, and they have all like dependency with each other. So this quite hard to handcraft one, and also determine like the call sequence, like you call A first and call B first. Basically, that's the motivation. And then what's our focus? Well, our focus is trying to starting from the result from the bug finder and trying to convert it to a POC. So this is a well-studied topic. Basically, it's called proof of concept exploit. So basically, you find a bug, you're trying to reproduce it. Which the idea behind it is first, you're trying to understand how the attack happened. So we want to know why there's a bug, and we want to know how to fix it. And then another thing is that this is a evidence that that bug is actually exists. So nowadays people just send their program to LLM and ask, okay, is there a bug or not? And then LLM said, okay, here's a bug. And then they further ask LLM, okay, show me a POC to prove it. So this is the idea behind POC. POC is the evidence that showed there's actually a bug. But our study, since we are using formalization, we can extend the topic beyond traditional POC. So what we can do, we can do detection and forecasting. So the idea is the traditional POC only ensure that the same bug have been retriggered. Okay, they create a contract defining some logic, and then they can retrigger the bug. However, the attacker contract they define does not look real. They might contain some duplicates, redundant, or dumb things. They don't look like an attacker. But if we can create something that looks real, then we can learn from it and use as a forecasting tool to detect potential risky code, a potential attacker. Also, what we can do, we can try to see, okay, we find a POC and we submit a patch to block the POC. That's good. But is there any other POC? Because we want to block all possible attackers' paths. That's the idea. So we are beyond POC, but we are still POC. That's the idea. So our solution is using LLM plus form method, form of verification, basically. So we first let LLM to understand the bug. We are the verifier report. It's something like the right-hand side. Basically, we send the code, the log in the right block, everything to LLM, asking to trying to understand what's going on. Even if the information is incomplete, which just asking to understand what it is. And then we use verify to check LLM's output. So we ask LLM, okay, learn from it and trying to generate an attacker. And then we check if the attacker really triggered the same bug. We formally check because we use verifier. And then if LLM generates something wrong, we find a way to tell LLM what's going on, what he understood, what mistake he made. Right, the code is like unreachable, or the code just simply incorrect. Okay, so our solution can be divided in 4 steps. First, we proposed a new modeling. So this bounded cross-contract verification is a new verification mode that can formally simulate the behavior between 2 contracts. So previously, every verification tool in smart contract, they verify each contract independently. So even if you send let's just use C++ as an example. So you send a file with 2 C++ class, but every time he only verify each one by each one. So it's independent. But we develop let's say a verification mode that helps to analyze the interaction between them. This provides a way to analyze the interaction between attacker and the original vulnerable code. That's the basis. And then we can continue our work. Then we guide LLM to generate a attacker. And then we validate it to check if there is a exploit path or not. If there is not, which means the bug reproduction fails, then we provide IO diagnosis for the regeneration. Basically, this circle. And here's our algorithm. We formalize a report bug as the tuple, basically where the bug is and what safety property he violated and what kind of bug type is. So, for example, in line 4, this expression have a overflow, something like this. So we formalize the bug as this. And we formalize the interaction. So a contract A called to a contract B. This interaction, we interacted in address binding system. I'm not going to show the formalization here because it's a little bit complicated. You can check my paper, but here's the idea. And so given a vulnerable and attacker contract, this BCCV, what we're going to do, if we check if an attacker path reproduce the reported bug, we provably find it. So if there's a bug, then we can use verifier to prove that there's a bug. Otherwise, we formally diagnose why. So if we cannot retrigger the same bug, then the verifier should report what's the reason. So either it's unreachable, so the line of code which contains the bug is unreached by the attacker generated, or it's called incorrect parameter, which means maybe the initialization is incorrect, or the function argument is incorrect, or the state is incorrect, anything else. So they all categorized in incorrect parameters. So what's our contribution here? So we shift, there's a keep shift here. So we are not trying to simulating the attacking the exploit, but we do it in a symbolic execution way. So in a traditional automatic POC generators, after you constructing an attacker, you need to try the combination of function call sequence and try different environment setup. What do you mean by this? So you have, since you don't have a main function, right? You don't have a main function. All you have is some functions and some variables, right? So what's the initialization of these variables? Okay, so what's the function call? How to combine this function call to trigger the bug, right? So that's the thing. Even if you generate the correct attacker, you still need to determine like how you actually trigger the bug. That's the problem. So previously they need to exhaustively try with different paths, try different combinations. So the solution is that they set up a simulating framework like Hard Hat Foundry. So the result will be a framework lock. And then what we're going to do, we don't actually run the contract. So we don't execute the code. So what we're going to do, we symbolically execute it in a formal platform. This formal platform is the BCCV. It's the verification mode we construct. So we are not trying to actually run the code, but we use verifier as a platform to analyze. So you can see here in the bottom right is a log. So the log is generated by the same tool, but now you can see all the detail have been provided. So you can actually see the Dove coin, which is the vulnerable contract, and the reproduction contract is the attacker. So you can see there the concrete interaction, like how the parameter have been passed, how the value have been set, how the function calling sequence have been determined. So that's a big change. So we don't actually run the code. We use verifier to decide everything. So here's our evaluation results. So since our algorithm. It's just a framework, so you can build on any existing smart contract verifier. So we try on 2 off-the-shelf verifiers, which is ESMC and SOCMC. So we try and we get very good results compared to the previous. Let's say we are a similar result, like 90.9% compared to 88.5%. So, but like the previous tool only cover 1 bug type, but now we can reproduce 6 bug types. So that's also another contribution. Anyway, so the summary. So our key contribution is we construct a formal platform to analyze the behavior between contracts. So we can analyze the interactions. And then we combine the verifier and I'm proposing a generate, validate, and reflect workflow. So that's the whole contribution behind that paper we published. So then we go to part 2. So since we have a platform, we can formally analyze the behavior of the cross-contract interaction. So we can now further study a topic called exploit variant analysis. Okay, so the motivation is here. So we got the idea of a POC is to help LLM to write a fixing patch. So given a POC, developer can write a patch to block all the corresponding type of exploits. So for example, you show a POC to calling function A first, then calling B, and then reaching C, and then there's a line of code that in C that has the bug, right? So what you can do, you can block A or block B or block C. You can just follow the logic defined in the POC. That's the whole goal of generating a POC. However, we now continue to ask, what if there are other types of attack? Is there any other POC that worth analyze? Can we find another POC? Does our patch fix everything? Does it block any possible POC? That's the question. For example, you can see down below here. For example, we have a certain failure. It can trigger by the overflow, but it can trigger by underflow. It can trigger by division by 0. Maybe this certain failure can be triggered for many possible reasons. So also you can see, what if a bug can be triggered via 2 distinct paths? So you call A first and call B, or you call C first and call D. So these 2 distinct paths. And if you only generate a POC for the first path, then you might miss the second path. That's the idea. So we call this a non-equivalence path, a non-equivalence POC. So this non-equivalence, we need to manually define it because they don't exist, this kind of thing. So it's basically it's a standard. So you can say it's by defining by different bug type, like you trigger by overflow, you trigger by underflow, or you can define it by different paths. So it's a standard, it varies. But since it's a standard, it's basically a formalization. So it's a standard and it's a formalization. So you need to define everything. So it fits our topic well. Also, if you want to show there's no more equivalence exploits, you definitely want to use formal verification. You need to prove there's no more exploits exist. Right? You need to formal verification. So traditional POC, including VeriExploit, right? They can generate multiple POC, right? That's fine. You can generate one, then you continue generating, continue generating. But they rarely check if this additional POC is really useful, right? Are they the same? Are they all blocked by the same patch? Are they really useful to finding new for new things? I say, right? So to set up such non-equivalent rules, we need to think from the bug fixing view, like what is a good POC, right? What we are expected from a POC, right? We expect where is the bug, what the bug looks like what type of the bug is, what's the precondition to reaching the deadline of the code, everything. So we need to summarize first, and then we need to pick what information is the key. And so if they change, they can be seen as a different or distinct POC. So we need to decide what information are the most important. And if they change, that means it's a different POC. And then how we prove it. So you might define something that we cannot prove it. So we need to choose something that we can formalize and prove. So here's a hypothetical solution. So after we finding a valid POC, right? After we find one, we send it to LLM, and alongside our predefined non-equivalence rules, like what we define as a non-equivalence. And then we ask LLM to generate a non-equivalent one. And after receiving the candidates, we then formally check, we still check if it can re-trigger the bug, but with an additional step to check if it's distinct to the obtained ones. So that's the first solution. It's quite simple. Just add one more check after the VeriExploit. And here's the second solution. So after we find the POC, we then need to prove that there is a path. Otherwise, we don't want to try it anymore. So we need to some extent, prove that there's some hope. There might be another path. And we need to use verify to check, to maybe just prove it there's another trace and then output it as a bug report, right? So we first find there's another trace. Then we send this trace as targets to LLM, just asking to fill the details, trying to convert this raw text to a concrete content. So now the LLM has a target. You just need to focus on that new trace. And then, the last step, we don't, the last step is we check if the POC is different from all the obtained one. Now we are going to do is if it's the same path we found previously. So we are basically validating different things between two solutions. Right, so that's our, let's say, ongoing work about extending our VeriExploit paper. But the third part, I want to talk about beyond smart contract, beyond bug reproduction. What's our thoughts about combining formal method and logarithm model in general? So when I was reading the paper, I always read some pure LLM study paper. Well, what they're trying to do is I generate a lot of things, right? And I can show that most of them are usable. So basically, I generate 100 contracts, and 90 of them are compilable and actually usable. That's their goal. But for a study that combining LLM and formal study, we expect less things, so we cannot generate as much as theirs. But what we can provide is a formal proof to show that all the generated ones are the thing I want. They are basically in two different goals. So a typical string of a LLM plus formal method is that you not only input your requirements, but you input a predefined standard. Anything, just this part need to manually decide. So like for our case, we define the standard is that you need to reproduce the same bug. That's our standard. So we formalize the bug, what the bug is. So we formalize it, and then we send it to LLM, and then ask you need to reproduce the same bug. That's our standard. And the formal text is that it's something help LLM to generate. It's like for VeriExploit example, it's the original bug report. Like even if it's a little bit too abstract, it is incomplete, but it's still a useful information for LLM to study. So it always has two things, and the output is an LLM output and a certified evidence as well. So the idea is we need to show that yes or no or unknown. So we need to show that our output is correct or not formally. So we have evidence to show that it's correct or not. So the goal is like we don't want to check anything afterwards. So even if most, like in a pure LM approach, everything, like most of the thing is correct, but something is incorrect, you always need to manually check and you filter them. Then that's the thing we don't want. We want a fully automatic approach. And then we need something, sometimes we need a clear interpretation for the output. What does it mean? Is like you generate something, but sometimes you don't know what you generate. For example, in this case, you want to reproduce a bug, right? So you generate a contract, okay? But you don't know if it looks real enough. You don't know if there's some dumb or redundant code. Basically have no knowledge. You're just trying to rerun on the simulating platform and see if the symbolic can be triggered or not. So you don't actually understand what you generate. But if you use formal verification, you have some evidence, and evidence helps you to understand. And also you can preserve some semantic during generation. This is clear. So before you send it to LLM, you use verifier to get some information, get some like invariants or some properties. And then after you get something back from LLM, you re-verify to ensure the invariant is unchanged and the property is not violated. So this is a simple idea. And here's some example of some application of this stream. So LLM generates codes and verify ensure that's bug-free. And LLM generate POC candidates, verify sure it's valid, so we reach the same bug. Or LLM repairs code and then verify, ensure some logic, some core logic, you don't want to change it, so they are unchanged. Or you can show that some you already know their part of code is irrelevant to the bug, so that part of code need to be unchanged. So LLM mutate the program. It's like mutation testing. So you inject fault into the program. So the mutated program, the verifier ensure the semantics actually change. So it's not a equivalent mutant. But we have some trade-offs. So LLM are good at handling big program, but verifier not. So verifier cannot handle big program. So due to the bottleneck of the verifier. So also, if the rule we manually define can be too strict or too loose, either way will make LLM generate less thing, or we might miss some outputs. Either way, even it's too strict or even too loose, we can miss something. So here's trade-off. So what we discussed previously is the formal method for LLM. Now we're talking about LLM for formal method. So as we discussed previously, so verifiers typically cannot handle very big program. Like it's because you need to convert everything into math and use the solver to solve it. It's hard. But LLM can handle big things. So the natural question is, can we use LLM to help verifier to handle large program? So we have some application here. So we can use LLM to generate or simplify the SMD formula, which there are already some studies have done this kind of things. So basically they are helping the solver part. So they give less pressure to the solver, less thing to verify. And another study is to accelerate the symbolic execution. I mentioned a paper here. It's published in ASC 2024. I mentioned it because it's published by our group members. So it's a contribution from our group. So the idea is using loop invariants. So you have a loop, and loop can be very hard to verify because you need to unrolling in a symbolic execution. If a loop have a need to unwinding too much time, there will be too much pressure for solver. So what we do here, we replace the whole loop by a invariant. So but basically it's two assumption. To assume and as a precondition, one assume as precondition and one assume as post condition. So you use two line of code to replace the whole loop. That's the idea. So LLM will try to propose this invariance. So we ask them to analyze the loop and propose. So this is the ASE distinguished paper. I think it's good study. But there's some trade-off. The trade-off is that a LLM verifier, basically a verifier integrated with LLM, may become reliable. Just take the ASC 2024 paper as an example. We use LLM, but we cannot ensure that their result is correct. So we don't re-verify the results generated from LLM because we can't, because we don't know the answer. It's different approach compared to our previous one. In the previous formal method for LLM approach, we have a standard, so we know what is correctly what is correct, what is wrong. But now we are just using LLM to generate anything, so we just hope it generates correctly, but we don't know if it's actually generated correctly or not. So that's the trade-off. But like I said, like most of the time they generate correct thing. That might be enough for most of the people. And thank you for listening. A big thank to our course. Reflection is like a chain of thought. Yeah, we wanted to use the name of train of thought, but some reviewer think it's not train of thought, so we changed the name to reflection. Maybe I should keep sharing my screen so anybody could ask question directly to the slides. I don't think I met anything like this. So you see, as a precondition of running a VeriExploit or any other POC, the precondition is you have already been able to find a bug. So since you already found a bug, which means I don't think there's any issue to reproduce it, because reproducing is to some extent is a more simple task compared to finding a bug. I have a question actually. So is everybody here familiar with formal method? Because I think I forgot to explain what formal method is. So okay.
I'd agree.
That's me.
Okay. Yes, I think we can think of my research like a explaining AI, because the core idea is provide an evidence.
Yeah, I think another parallel in security is like what we call bug minimization. So when you want to report a bug to a uh, to someone and show a proof of concept, like they usually require like a very simplified version, and fuzzers usually find a really complicated input string, right? So then bug minimization is like another parallel over here, and I think this could also be used for that.
Yes, because it's a characteristic from the verifier, because verifier always find the bug in the simplest approach, because he let's say, not to say verifier, let's say model checker, because they are trying to unwinding the program, right? So unwinding one by one by one. So they trying to flatten the program layer by layer, and then this method ensure that he always find the simplest approach, and like not always, depending on how the verifier is implemented. But in theory, you always find the simple way to reach the bug. However, that's from the verifier side. You cannot ensure the LLM will generate something that's 100% reflects your context. So you report a context example, you report a trace, a log, which is very short, right? As the simplest way to reach the bug. However, LLM can generate anything basically. So in our framework, like the VeriExploit, our solution to this bug minimization is, even if you generate something, but thanks to a verifier, because we are still using verifier to validate if there's a valid path or not. So if it's valid, the output is still a verifier report, which means it's still the shortest one. So I think this is a good point comparing to the simulation solution, because simulation solution you need to like traverse every possible combination. Then it looks like a fuzzer, so you need to traverse the path.
So I have a question. Is the sort of targeted use of this approach mostly in sort of offline context where you already have bugs identified, as opposed to contracts in the wild?
Sorry, I don't understand the question. Can you
So would
explain a bit?
could this method be applied to contracts in the wild, or just things that you've already identified as a bug, like pre-screened and as input?
You need to already know there's a bug. The bug
Okay.
have already identified. Yes. Yes.
Yeah.
Yeah.
My angle there was sort of whether or not, if this is sort of deployed in the wild for that automated discovery, whether prompt injection could be a concern if you're going through LLMs iteratively. Yeah.
I think this is a good question because I think this is a question asked by my reviewer in the one of the reviewer in the rebuttal. So the questioning that's why we don't considering the deployment environment. So when we consider what the environment looks like on chain. So first of all, our solution is mainly focused on source code. So you use because the input is a report from the verifier. The verifier needs source code. So our solution is based on the verifier. So you need to be on source code. Another side is that it's like a moral issue. So it's a ethical issue. So basically a POC generator is a attacker basically. So yeah, so you don't. Yeah, 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 sure. Okay, thank you.
Thank you.
See you.